Acid and base chemistry is found everywhere from manufacturing to biochemistry, but it gets somewhat convoluted when all the different possibilities are considered. There are Bronsted-Lowry bases, Bronsted-Lowry acids, Lewis acids, and Lewis bases. Yet how can their inter- and intramolecular reactions be told apart? A Bronsted-Lowry acid donates a positive hydrogen ion, a Bronsted-Lowry base accepts a positive hydrogen ion, a Lewis acid accepts a negative electron pair, and a Lewis base donates a negative electron pair. Thus, both types of bases become more positive after their reaction, and both types of acids become more negative. It's important to think of magnets. Opposite charges enjoy one another's company. How these acids and bases are told apart actually depends on the reactants involved, as molecules like water can act as Bronsted-Lowry acids or Bronsted-Lowry bases, depending on the other reactant's acidity or basicity. But something which is more basic will enjoy becoming more positive, something which is more acidic will enjoy becoming more negative, and the strengths of the acids or bases could be determined by how close to neutral the resulting products or conjugates are, discussed later in this video. Strong acids are acids which give up all their hydrogen ions in a solution, as in the Bronsted-Lowry definition. Such acids have hydrogen bound to really electronegative atoms, electron-loving atoms, so the atoms don't mind giving up positivity in the form of a positive hydrogen ion. There is a list of these, and there is also a list of strong bases, which in contrast have less electronegative group 1 and 2 atoms that easily hand over their electrons to their OH group and afterwards release all their basic OH groups in a solution, but many substances do not fit into these categories. For substances which do not meet the definition of strong acids or strong bases, some clues can be drawn from their structure to determine which types of acid or base one may be. For example, does an atom in the molecule have a pair or pairs of electrons which are not bound to another atom? If so, the atom with unpaired electrons may be coaxed to give those up, as in the Lewis base definition. However, halogens are very electronegative and will not behave like this with their unpaired electrons. Azo dyes rely on the donation of neighboring unpaired electrons when struck by a ray of light in sending back the light, producing the spectacular colors many of our clothes are dyed with, and beta-carotene works the same way, giving a brilliant orange color to carrots and leaves in fall. Thus, groups with unpaired electrons, such as with the oxygen in an OH group or with the nitrogen in an NH2 group, will also share electrons easily, making an aromatic ring or conjugated system more basic. Such movement of electrons, or resonance, can also cause substances to be more acidic if the hydrogens are attached to an atom which is attached to a withdrawing group with pi bonds, as with a carbonyl group, where a carboxylic acid may easily give up its positive hydrogen ion and become stabilized by the molecule's ability to share electrons, allowing the hydrogen ion to leave more easily. Since the movement of electrons is able to stabilize the structure, the effect is either more basic or more acidic, depending on the arrangement of the atoms. Similarly, if the conjugate or product of acids or bases is more neutral, this helps drive the reaction forward, comparable to how an exothermic reaction is more favorable and spontaneous, and the strongest acids therefore have the weakest conjugate bases, while the strongest bases have the weakest conjugate acids. Once the acidity or basicity of the reactants involved is determined, it is easier to figure out if the reactants will act as Lewis acids, Lewis bases, Bronsted-Lowry acids, or Bronsted-Lowry bases.